Hey all, today we are going to continue our discussion on sample proportions, and we're going to talk about building confidence intervals. So we're going to work through the example on page 490, number 11. So if you have your book, you can read it from there, or you can take a second and read it here. So you can pause and read this problem, and then we're going to use this problem to discuss what exactly is a confidence interval and how can we construct one. So we're talking about mislabeled food packages, and in these 190 packages of seafood, they found that 22% of them were mislabeled in some way. So the question is, does that mean that all of the seafood packages that go to these restaurants or stores, uh, is that the real percentage of packages that are mislabeled? And your gut answer is probably correct. The answer is no. This was just one sample of 190 packages of seafood. What we would do is we call this a point estimate. It's an estimate of the true percentage, but it's not the actual true percentage. We've only taken a sample of 190 packages. And so if we were to have sampled another 190 packages, we probably would have gotten a different percentage of packages that were mislabeled. There's variability that exists in the world, and so that's why we can't say for sure that 22% is the exact percentage of all mislabeled packages. So because we want to get sort of a better idea of where does the actual population proportion lie, we build these things called confidence intervals. An interval has an upper and lower bound, and we'll look at numbers in between those two values. And we're going to do that with a level of confidence, which I'll explain more as we go along here. It's sort of like casting a net uh, to try and be more informed about where our true population proportion is. So you could fish with a fishing hook, or you could fish with a net. There's probably a better chance of catching fish if you have a net than it is if you have just a single fishing hook. So this is the structure of a confidence interval for one proportion. We'll call it a one proportion Z interval. Hopefully you are thinking that that Z might be related to the normal model, because it is. In this case, we call it a Z star. That star isn't a multiplication sign, it's attached to the Z. Z star is a critical value. It's a Z from a normal curve. We call it Z star in this situation. P hat is a proportion of a sample. We've dealt with P hat before. Q hat, we would subtract 1 minus P hat to get Q hat, same as we did before, and N is the sample size, same as we did before. Notice we have a plus or minus here. I said earlier that when we build an interval, we have an upper and a lower bound, so we're going to get two values that create our confidence interval. And so I want to talk a little bit more about the structure of this formula before we move on and use it. So we sort of had two big pieces separated by this plus or minus. We have our point estimate. That's the value or the proportion we get from our sample. So in our case, 22% of mislabeled packages out of 190. In this part on the right here, Z star times the square root of P hat Q hat over N is the margin of error. And then if we break that margin of error down a little bit further, that square root is what we call the standard error. We were calling it, when we talked about the distribution of sample proportions, we were calling it the standard deviation of P hat. And so when we're building a confidence interval, we're going to call it the standard error of P hat. It's essentially the same formula, except in this case, we're using sample proportions to find this value. back when we were talking about the distribution of sample proportions, we had some sort of idea of what the population proportion was, and we used regular P, regular Q. So that's why we call it standard deviation. Here, since we have just values from a sample, we call it a standard error. So again, we have this whole formula broken into pieces. We have our sample point estimate, we have our margin of error, and then that margin of error broken down even more, we have the standard error. And again, Z star is called a critical value, and we're going to be able to calculate that, which I'll walk through with you. So just like when we wanted to use a normal model with the distribution of sample proportions or the distribution of sample means, we had to satisfy some assumptions and conditions so that we could deem it appropriate to use a normal model. These assumptions and conditions today are going to be the same as we had for the distribution of a sample proportion. We need to have a random sample or have done a randomized experiment. We need our individuals in the sample to be independent or less than 10%. And we need to meet this success failure condition where n times p and n times q are both greater than or equal to 10. So we need to expect at least 10 successes and 10 failures. So in the scenario that we're dealing with here with this seafood, the success is a mislabeled package. So in our sample, we need to expect at least 10 mislabeled packages, and we need to expect at least 10 non-mislabeled packages. So out of our 190, we had 41.8 approximately mislabeled and 148.2 not mislabeled. So we meet that criteria. And we did have a random sample. We assume those 190 packages are random, and that 190 packages of seafood is less than 10% of all the packages of seafood being shipped to restaurants and stores. So since we've satisfied the condition, now we can start building a confidence interval. So we always start with the formula. And now what I want to do is call out each piece, so all I need to do then is plug in the values and simplify. So our p hat is our 22%. Give it in the problem, 22% of all packages were mislabeled. Our q hat is 1 minus p hat, so 1 minus 0.22 is 0.78. So that means that 78% of them were not mislabeled. N is our sample size of 190 packages of seafood. And so now we need to do, we'll call it the hard part, I suppose, is calculating Z star. So this is where, when I say 95% confidence, this is where that 95% comes into play. Because based on our confidence level, our Z star is going to change. So some typical confidence levels are 95, 99, 90, maybe sometimes 98. We could do any level of confidence that we want, but those are the ones that you'll typically see. And that level of confidence is going to change this value, Z star. So what that confidence actually is an area of the normal curve. And it's the middle area. So we're looking for what Z value, plus minus, because this is symmetric, they're going to be the same absolute value. Which Z values cut off the 95% area in the middle of this standard normal model. If 95% is in the middle, then there's 2.5% left over on in each tail. Because this is symmetric, the area is going to be the same on both sides. So we can find the Z value on our calculator by doing second vars inverse normal. And let me pull up the calculator so we can do it. So I'm going to do second vars choice 3 inverse normal. So when we do the regular normal CDF, it's going to tell us the area under the curve. If we want to use the area to find a z, then we're going to use inverse normal. And what we need to tell the calculator is we need to tell it how much area is to the left of this positive z value that you want to know. Well, if there's 95% in the middle and 2.5% on this tail over here, then there's 97.5% area to the left of this positive z value. So that's this little calculation here. So I'm going to tell it 0.975. I'll leave my mean and standard deviation as 0 and 1. And then I get this as a z. This is the z that cuts off this center chunk that is 95%. So I'll round it to 1.96 like I did here. That's our z star. That's our z value, our critical value associated with 95% confidence. Anytime we do a one proportion z interval, if I'm looking for 95% confidence, this z star is going to be the same. So you might start just remembering some of these common z stars, these common critical values. So for 95%, for one proportion z interval, we're always going to use 1.96. If you don't remember that, it's okay. We can always calculate it like we just did. So now I have all my numbers. I'm just going to plug them into the formula. I got my p hat, z star, p hat, q hat, and n. I'll simplify my standard error. That's everything underneath the square root. That piece is the standard error. Multiply that by my critical value. That 0.0589, that represents the margin of error. And now I'm going to add and subtract that from my 22% point estimate. And we end up with an interval that we present in parentheses. It sort of looks like coordinates, but that's how we present the interval for a confidence interval. Smaller one on the left, bigger one on the right. So my interval ranges from 16.11% to 27.89%. So finally, let's talk about what these numbers mean. And it's very important to get the wording right here. We don't want to say something that's not true, so we're going to work through that. So we're going to be 95% confident that the true proportion of mislabeled packages that we don't know, we're just trying to get an idea of what it might be. We're 95% confident that the true proportion of mislabeled packages of seafood in stores and restaurants, so I add my context in there, is between 16.11% and 27.89%. It's no guarantee that the true proportion of mislabeled packages is 22%. It's no guarantee that it's between 16.11 and 27.89. But what we can say is that we have this 95% confidence level that it would be in between those two values. It's more likely than not that it's somewhere between those two values. So finally, I want to explain what does it mean to be 95% confident. It doesn't mean that you just feel good about it. So we sampled 190 packages of seafood. If we were to keep sampling 190 and 190 and 190, and we got every possible combination of 190 packages of seafood, which you would admit is totally impossible. But if we did that, and we created the confidence intervals just like we did here, 95% of those confidence intervals would contain the true population proportion. So impossible, impractical to actually look at every piece of packaged seafood and figure out the percent that are mislabeled. Impossible, impractical to sample 190 packages of seafood and then do that for every combination of 190. But if we did, 95% of those intervals would contain the true population proportion. So instead of doing that, we can do it once with one sample, and we could have this level of confidence associated with it. So I have a few questions for you related to page 490, number 15. Make sure that you answer those questions. If you have questions while you're watching this, please make sure that you ask for help, and we'll absolutely spend some time together working through this process, working through the ideas, and getting better at it.